Hello students, in our last video we looked into two equations famously known as Richards equation and Phillips equation to estimate rate of infiltration. We also mentioned that both these equations can be developed as an approximate solution of Richards equation. And whenever we are making these approximations, we are simplifying some assumptions that we make, or we take the assumption that everything is homogeneous both in space and time. But what we need is an alternative approach, which is better approximation of physical theory, but it has an exact analytical solution. So to address this gap, in 1911, scientists named Green and Ampt, they develop a new methodology to estimate the rate of infiltration in soil strata. So we will try to look into that model and try to develop more intuition that what this infiltration is and how we can develop better models to estimate that in both in field as well as lab setting. So here we will consider a parcel of soil, and uh, before precipitation has started, let us say that it is in unsaturated state. Now, when it is in unsaturated state, that would mean that both air voids are present as well as some water molecules are present. Mind it, I am not saying that it's completely dry, but it is unsaturated. So we can say that total volume of voids is equal to volume of water plus volume of air. And if V is the volume of this soil block, so that will comprises of volume of voids plus volume of dry soil particles. Now, uh, as this water starts infiltrating into the surface, what would happen is that this infiltrating water will try to occupy all these air voids that are present and replace them with the water molecules. And up to depth L, as this infiltration continues, we would have a two-phase system in which we will only have water and soil particles, because if we say that now that saturation has taken place up to L, all the air voids would be expelled and they would be replaced by water molecules. And the theoretical limit that up to what when saturation happens, the maximum amount of moisture that can seep in into a soil parcel should be equal to neta or porosity, because porosity basically tells us that what is the volume of voids per unit volume, and theta is volume of water divided by V. And when this soil parcel reaches saturation, we essentially say that our porosity has become equal to the soil moisture content, or VV has become equal to volume of water, which also tells us that our degree of saturation has become unity. Now, using these fundamentals from soil mechanics, what we can say that if some initial soil moisture was present, let us say theta I was the soil moisture content at T equal to 0, just before precipitation started happening, and neta is porosity of soil sample, and we are assuming that properties are more or less consistent here. That means for a given soil sample of small volume, these neta and theta can be approximated by one single number. So the total amount of water that will infiltrate in time t, it should be equal to neta minus theta I multiply by total volume of the soil sample, which should be equal to neta minus theta I multiplied by area into length, and this is the length up to which saturation has happened. And this phase that is moving downwards, because if more and more water keeps on entering into the soil, that would mean this wetting front that is developing at the interface of recently saturated soil and unsaturated soil just below it would keep on moving forward, and hence L is the length of that strata that which has already saturated. For unit area, we can write this as neta minus theta I into L, which is equal to Ft, and this Ft is the cumulative amount of water that has infiltrated. Now, we also learned that Q is equal to minus K H2 minus H1 divided by Z2 minus Z1. And we also mentioned that infiltration is nothing but it is a negative q, because we say that infiltration always happens in negative downward direction, and we were having the convention that our positive z direction is this one and negative z direction is this one. So we can safely say that q is equal to minus f in magnitude. So we can write this as minus k h2 minus h1 divided by z2 minus z1. And this h2 represents some head that is present at datum. So if we take this level as h2, we can say that if the depth of water, just because of the precipitation that is happening, is h naught here, so we can say that at z1 equal to 0 meter, if I take this as a datum, my head is h naught, and at depth of minus L meter, which is Z2, our depth is going to be minus L minus some suction, because at the interface we still have unsaturated soil which is going to possess some suction. So when I substitute these values of H2, H1, Z2 and Z1, I end up with an expression which looks like F equal to K into H naught plus phi plus L divided by L. I am doing nothing special. These minus goes away and just substituting the value of H2, H1, Z2 and Z1 and so on. So this is what we get as the rate of infiltration, and this is the cumulative volume of infiltration that has happened. And now we have to relate 1 and 2. For sake of simplification, we can write Ft as L times delta theta, where delta theta is nothing but it's the difference between porosity and initial soil moisture content that is present, and both these quantities are measurable in the lab, which implies we can define L, we can write L as Ft upon delta theta, and this becomes 3. Now what we will do, we will substitute 3 in our equation 2, and we end up with the expression that F equal to K into phi plus F upon delta theta divided by F upon delta theta. So I'm just dropping this subscript, this bracket term T for sake of simplification, but whenever we write F, that means how much infiltration has happened in time T. We also know that differentiation of total volume of infiltration or total amount of infiltration that has happened is also equal to the rate of infiltration. So df upon dt is equal to small f. So we can write this expression as df upon dt equal to k times phi delta theta plus f divided by f. And this is based on the assumption that this H naught is much smaller than phi plus L. That means that not significant amount of water has stagnated on the surface and runoff is happening if it is not able to percolate into the water. So under that assumption, we are able to simplify the expression by dropping this H naught equal to 0. Now what we will do, we will try to solve this integral. So we will write this in a form that this is f upon f plus phi delta theta, and this would be integrated df, this would be k dt, and we will integrate it from time 0 to t, and f from 0 to what is the total amount of final amount of f that has entered into the soil. Now what we will do, we'll use method of partial fractions. So what we will add and subtract phi delta theta minus phi delta theta, and we will divide this by f plus phi delta theta. This would be f plus phi delta theta times df equal to kt after substituting the limits, and here we have to still perform the integral from 0 to ft. And when we solve this integral, you can clearly see that this term will reduce to 1, so this would simply become ft after substituting limits, and second term will become phi delta theta into ln of f plus delta theta times phi with the limits of 0 to ft, and this is equal to k times t. And when we simplify it, we can write this as ft minus phi delta theta times ln of 1 plus ft phi delta theta equal to kt. And this expression that is used to calculate what is the total amount of infiltration that would take place in the soil with more exact solution but with reasonable assumptions is known as Green Ampt's method to calculate the rate of infiltration. Now you see that the beauty of this method is that most of these quantities are measurable. For example, suction we can measure. We can also measure porosity. We can also measure what is theta I, that is initial amount of moisture that was present. And that's why we say that this model can be used in the field to come up with the better approximations of rate of infiltration. Now, another important concept that we need to discuss in this context of Green-Ampt's method is called as ponding time. So all the methods that we have been discussing so far about infiltration, they are based on an assumption that water is available in form of precipitation, and hence whatever rate of infiltration is happening is maximum or potential infiltration. This concept is very similar to what we discuss as potential and actual evapotranspiration. That means that we assume that moisture is present and hence evaporation can take place. Similarly, this is the concept of potential infiltration. But let us say that our soil has the infiltration capacity F naught as 3 mm per hour, but precipitation is happening at the rate of 2 mm per hour. Then if somebody asks us how much infiltration will take place, then answer is obvious that although the capacity is 3, moisture that is available for infiltration to happen is only 2 mm per hour. So we would say that while potential infiltration is equal to 3 mm per hour, actual infiltration that is happening is 2 mm per hour. So another question would arise that up to what time this infiltration would occur at non-potential rate. And what that means is that if we plot the infiltration curve, it would look something like exponentially decaying if we go by Horton's, or even if we look at the Green-Ampt's formula, it also takes an exponentially decaying form. So this is going to be an exponentially decaying function, and this is a variation of potential infiltration. If actual precipitation is happening at the constant rate of I mm per hour, and this is also F, which is rate of infiltration, this is time, you can clearly see that until this potential infiltration curve and this constant rate precipitation curve intersect each other, precipitation is going to, infiltration is going to happen at the reduced rate, or whatever is the rate that is prescribed by the precipitation occurrence. Now, after this intersection happens, what would happen is that precipitation, let us say, is continuing at the same intensity of I mm per hour, but now less water would be able to infiltrate into the ground. So at this time point, ponding will start. That means water will start accumulating on surface, and we are interested to measure this time Tp. So we already developed an expression of Ft, that is Ft is equal to K times phi delta theta divided by Ft plus 1. And question is, can we determine at what time this ponding will start? That is when the precipitation rate curve and the potential infiltration curve will intersect. Now it is fairly straightforward. So what we will do here is that Ft would happen when rate of infiltration becomes equal to rate of precipitation. So this should be equal to I. K is property of soil, suction is property of soil, And moisture deficit, neta minus theta, is also property of soil. So we will keep them untouched. Total amount of infiltration that will happen until this intersection happens is definitely going to be I multiplied by TP, because whatever is happening, soil is thirsty. Soil can absorb this much, but actual moisture that is available is lower. So it will absorb all the water that has happened or fallen onto the ground. So that is going to be ITP. So we will write this as I times TP, and this is I is known, phi, theta, k we already talked about. So we can easily estimate that what is the time at which ponding will happen, which is given by k into phi delta theta divided by I into I minus k, and this is known as ponding time. And this ponding time also gives us an intuition that why runoff would start generating, and our next few chapters will specifically focus on estimation of the runoff. So moving ahead, we will discuss an important index called as phi index, because all the methods that we have discussed so far, they are very much into hydrological sciences. That means we need a lot of information about data sets, we need a lot of information about soil properties. So the question arises, is there any crude or approximate way to estimate the runoff? Runoff is water that is running away after all the losses from given hydrograph, without using so many equations and so many parameters. And we will try to understand this concept of phi index into our next video. Thank you.